Okay, so first announcement is that my office hours have changed. I used to have a Wednesday after, like today after class. I'm going to switch that to Thursday. So I will not have office hours today or any other Wednesday after class. With the exception of on exam day, we'll try to work something out. So on exam day, I'll try to give you some way to come see me, get some help on exam day if that's. And our next exam is a week from today. A week from today. Okay, that's the first announcement. Next announcement is, okay, this is where it's getting tough. This is where you got to put your nose to the grindstone. Is that the right expression? Okay, so this assignment for Friday is longer, okay, and it's harder, and so we really got to pay attention in class today. But it's profound, okay. This is what we've been working so hard for like 6 weeks. So you got to really pay attention in lecture today, and really start this early, and give yourself lots of sittings on this. Give yourself the chance to go see. There's graphing calculator stuff in this. Give yourself the chance to visit a TA or myself. Okay? So I just want to forewarn, don't wait till Thursday night at 10:30 p.m. to start. That's not going to happen. Okay? So be warned. And then our exam is next in the exam prep area. Exam prep. I've posted the outline of concepts. Okay? It's a comprehensive outline in case you wanted to start looking at that now. For sure, you want to start your studying this weekend. The exam 2 is harder. Okay, we're actually just about doing calculus now. Okay, so it just kind of happened as we made this progression of ideas. Okay, but next week for sure we are doing calculus, and it's all on the exam. So check that out, and then we'll have like this weekend, early next week, I'll have all the homework solutions and quiz solutions updated on Blackboard. I'm not sure, we may be a couple behind right now. Okay? Any questions on this kind of stuff? Announcements? Yeah. Yeah, so this exam is longer and it's more difficult. As you can tell, that the material is getting more difficult. Okay? Other questions? Our goal is the general idea of this file that you're going to create right now is to graph a rate function and then have it graph a step function according to the parameters that we set. Okay, so where it says 1, 2, 3, 4, 5, you're not going to do that. That's just to instruct you on what you're doing. You're going to all you have to do is the command lines to get this graphing calculator thing to work. Okay, so I'm inserting those 1, 2, 3, 4, 5 to explain to you what the next command line is. Some of those command lines I've given to you. Some of those it's up to you to know what it is and how to do it. Okay? So we're just going to give you 10 minutes now. I'll make the text bigger as you get started, and we'll come around and try to support you. But follow the instructions. Remember what you learned, both about the step function and rate functions and graphing calculator, and see if we can make it work. Okay? So. Again, some of them you're just going to copy as is, like the number 1 and 4 I'm giving you. But 2, 3, 5, 6, and 7, they're up to you to determine what those command lines are based on the mathematics we're doing and your recollection of how graphing calculator works. You didn't forget it, right? Okay, here we go. Go for it. Okay, so let's see how we're doing here. So how do I graph a function that I've defined? So I've defined this function, this rate function, capital R. How do you graph it? Y equals R of x, right? So that's going to take all the x values on our x-axis, give us the corresponding y's, which we know is a bunch of points, right? Which makes a curve. But we want to do it for starting from A. Remember how to do this? We did this. How do you now cut off or just show part of a graph that you're wanting to graph? Comma. We just want x greater than or equal to A. No, if doesn't really make sense. It might work, but that's not really the way what if is about. Okay, And so we've got that. We're setting delta x equal to 2. If you didn't get this, it's okay. We don't want to spend time on it. All right, so left x, who has learned something? How am I? So got left, control 9, right? I'm defining a function, need control 9, x. What is left x? A plus floor x minus a over all times. Okay, we worked hard on that. You worked hard on that in your homework, right? So we did that Friday and Monday, and then you had homework on it. That's the left function. What that gives you, if you put in any current value of x, it returns or outputs the x value at the left side of that current interval. And now we've seen that's in terms of making step, that's really important. All right, so now we want to define step. In one expression, one expression rule. Who's learning something? What is step? So it comes from the rate function, control 9, left. We're taking the left value and putting that into R to give us that constant rate across whatever interval we're in, right? Because within a given interval, that left x value will be the same every time, and then you'll get the same rate out. So it'll be a constant rate in that interval. Okay, so now how do we graph step? Y equals step control 9 x just for greater than or equal to a. All right, so I'm going to turn this on. Red for rate, and blue for the step, and let's see how we did. What's that? Control colon. Something like this. How many people were successful? Oh, good. If you weren't, there's no way we can troubleshoot all of you. Just have to do it outside of class. So just pay attention. There's lots of syntax in there. You have to have it right. If something went wrong in your command lines, then this might not have occurred. So I can't address individual issues. But do you have a question?
I just don't have little dots.
Did you do line 4? That was the optional line. That was the optional line. Put the red dots. Mark off. Yes, you didn't do the optional line 4. You won't have it.
Why are there little lines?
Yeah. Okay. So, does this look like the step function that we want? No. Something's wrong, right? Something's wrong. What's happening here? How does Graphing Calculator create graphs? Well, it creates them just by what they are. What are they? They're points, right? So it graphs a bunch of points, and then it connects the dots. It's just that the points are really close together. So what is it doing? It's coming to the end of this step, and it's saying, oh, the next point's up there. So what does it do? It connects the dots. We don't want that, right? Our step function is just these horizontal constant rates. It doesn't make sense to connect one step with these vertical lines. So here's how we remedy that. When we graph step, right here, put the cursor right here, we only want to graph step if our x value isn't a left x value. We want to graph it everywhere except where x is equal to an endpoint or a breakpoint, and that's at the left x value. So we can say if x, okay, and then if you do command equals, option equals, we get x is not equal to left x. Anyone PC, not equal to. PC. Tell me, what is it?
Oh, I don't know.
Yeah. Anyone figure out not equal to on PC? Sorry, I wasn't ready for that. What is it? Control Shift N?
Yeah.
As in Nancy. Control Shift N is Nancy. Awesome. Okay, so what is this going to do now? It's going to graph step x everywhere except at the left x points, which we know left x would be all the breakpoints. And so this should hopefully remedy and take off the vertical lines.
Should these be instead of function parentheses?
Which?
You have they're both inside of whole cell.
That's not a function.
Yeah.
But you don't have to put that. You can just type it. They just pop up. Okay, so I just want to show you one thing. Here's the beauty of this. Many of you have thought about, or it's kind of clear. Is this a good approximate rate of change function for the red rate function? Is it good? No, it's deviating a great deal from the actual rate. And we're trying to get a constant rate function that mimics or pretends to be that red rate function as good as possible. So how can we make a better pretend or simulated constant rate function? Yeah, so here's the beauty of this. Everything shrink delta x, they said, makes delta x smaller. But everything we've defined is based on delta x, so all we have to do is come up with the command line 3 and change delta x to say, make it 0.6. And everything works automatically. Everything we did for that step function was based on delta x as a parameter. So you just change the value of it and it changes everything. So there's 0.6. Is this a better estimate or better simulated rate function? Yeah, it's pretending, it's doing a better job pretending to be the function. Or you can do 0.06. All right, so look, hold on. Shh. That's 0.06, and I'm going to turn off the original rate function. What do you see? This is a constant rate of change step function. I've turned off the original rate function. What do you see? Blur your eyes. It's like the original rate function, see? But it's constant rates. It's a bunch of constant rates doing a very, very good job of mimicking the original rate function. But they're all constants. They're all constant rates. Okay, so now we're seeing this is the power of graphing calculator to do this kind of stuff for us, to help us understand what's going on. Smaller delta x gives a better approximation. And this is really good, right? People in the back probably can't see the difference between this and the original rate curve. But those are constant rates. That's a step function. Okay, so do visit us in office hours to get if you've got issues with graphing calculator, we want you to get those ironed out. Do please visit us, okay? Questions besides like technology troubles? Any questions on the, yeah?
Can you explain command line 4?
After class. Yeah, that's optional. So I don't want to spend a lot of time on that because we got much more important things to cover, but I'm happy to do it outside of class. Other questions? Okay, here we go. All right, so you can, if you don't use your laptop for taking notes or anything, you put that away. So what we do in the next half an hour, 25 minutes, is really important and a little bit hard. Okay, so please really try to dial in here, tune in. This is all this stuff is really important for exam 2, and even more important for calculus. So we're going to start with a bunch of review questions. These questions feel like review, just to make sure that we're all up to speed. Okay. So here's a graph. It concerns a value y of some quantity with respect to another quantity whose value is x. So there's some quantity here we're representing by y, and this graph has to do with that. Okay, this graph has to do with that somehow. Okay, and then I have a sum here below the graph. Okay, let's just start with these. So, what kind of function is the curve? Rate of change, the actual rate of change function. So that's in the context of what we've been doing. Okay, what's the input? X is the input, output is? Is it Y? No, it'd be the rate of change of Y, right? It'd be the rate of change of Y. Y would be our accumulated quantity. Okay, so it'd be the rate of change of Y. What kind of function is the step graph? Rate of change function. Is it accumulation? No, right? It's trying to be like R. It wants to be like R. Looks up to it, right? So it's a rate of change function. Okay? So what's the input into step? X. What's the output? An approximate rate of change of Y. An approximate rate of change of Y. Why do we want that? Here's an important question. We better know by now. Why do we want that?
To simulate a constant rate of change on certain specs.
But why do we want constant rates of change?
So that we can solve for H1.
Yeah.
Oh, I was kind of like to say that. So we create a step function to find a constant rate for any interval, no matter how many intervals we have.
Right? For what?
To find your accumulation.
Yeah, because with constant rate of change, we can calculate accumulation. If the rate's continually changing, we have no means of calculating accumulation. Okay? But actually, that's what we're doing. That's actually what we're doing, trying to figure out how can we get accumulation for a changing rate. Well, all we know so far is how to do it for a constant rate. So that's what we do. Okay? So what are the specifics of this particular step function? Shout them out. So what is the step function about? There's parameters around this, right? So what are they? What's that?
1 to 3. Or 0.
Okay, so showing from 0 to 3. But what about the step function? Mid. It's based on midpoints. What else? Delta x is 0.3, right? So delta x 0.3 is based on the midpoints of those intervals. That's where we're getting the rate. Okay? So we want to represent, so looking at the third interval, where does that value of step come from? In the third interval, the value of step comes from? So here it is. So 1, 2, 3. So where does this value of this rate of change come from in this third interval? The midpoint between them. So we could write it as? It comes from the R function. This is key. We all should know this by now. It comes from R. What about R? No, not the left. This is mid. So what is the mid? It's the third interval, halfway between 0.6 and 0.9. How many people got that before I wrote it? Not enough. This has to make sense. It's coming, if it's mid, it's coming from the rate at the midpoint of the interval. The midpoint of the interval is 0.75. So we need that rate to be the rate for that whole interval in the step function. Because they're coming from the middle. They're all based in the middle of the... It's the mid function. You see? See it? This is not based on left. This is based on mid. Based on mid. That's what. Yeah. So that's what we talked about for number 3.
In this case, in this instance, can you put 0.25?
0.25.
Yeah, because like the K is not like at that it's 0.25. Like would that be right? Or said that?
No, this step in the I'm not sure what you're thinking. That 1, 2 in this third interval, that rate is determined only by this x value, the actual rate at the midpoint of the interval.
Yeah, the rate is 0.25.
No, but that's not exact. You're just guessing. You're just picking it off.
Okay.
I'm saying exactly. Right?
Alright.
So it's exactly, it has to be a function value. Otherwise, you're just guessing. Yeah, but maybe it's close to 0.25. Yeah. Yes?
Is there an advantage to using left or mid?
So left is convenient because it's the starting point of the interval. But it's not. There's none is better than the other.
Okay, so you can just pick there on.
Yeah, but we're going to do mostly left, like we define left, and we'll stay mostly with left. But we look at right and mid as practice for our understanding, but we deal mostly with left. Other questions? Okay. What does it have to do with this? What does that value R of 0.75, our step, have to do with this sum right here? Anyone know? Looking at this sum, what does it have to do with it? Which interval is it? Third. What does it have to do with this right here? It's K3. K3 is our constant rate in the third interval. That's what that thing is. It equals K3. Does it make sense? Okay, so a rule for step X. A one expression rule for step X. R comes from R of mid X. X goes in. X is assigned to the midpoint in that interval, and then we take that rate for the whole interval then. Okay, so looking at this sum, what in this sum shows the accumulation from 0 to 1.2? What in this sum shows the accumulation from 0 to 1.2? So that's right here. What? We're going on for time's sake. So what does, if we want to accumulate starting at 0 up to 1.2, what does this big sum have to do with that? Specifically want from 0 to 1.2. How many intervals is that? So if I want the accumulation, what am I going to do? Add up to. That will calculate the accumulation from 0 to 1.2, the first four terms. Each of those terms is the associated accumulation with that approximating rate. So K delta X plus K delta X. How do things accumulate? Bit by bit. How is each bit calculated? K delta X. So delta Y plus delta Y plus delta Y plus delta Y. K delta X plus K delta X. Okay? So now what about from 0 to 2.2? Now I want to do from 0 to 2.2. Talk about that. I'll show you 2.2 in the graph. These black lines on. Okay, so hopefully you realize there's a difference now. It's not just add more intervals, right? There's something else going on here. What's different about 0 to 2.2 from 0 to 1.2? Yeah.
Does it define the middle of the interval define the rate at 2.2? It's by the middle of the interval.
Isn't that for all the rates, what you just said? Isn't that true for all the rates?
So at 2.2, it was the left and the right. You have to have the
Okay, thank you for thinking you're on the right track. Kenny.
You have to go to K of 8, but instead of the change in X being 0.3, it's 0.1.
Good. Okay, so we're going to do, I'll do it in red. So yes, we're going to add up the first 7 intervals, but that's not enough. But the full 8th interval is too much, right? So 2.2 ends up somewhere in the middle of an interval. So we're going to use, like he said, we're going to use K8, but this will be smaller. What will the delta x be? It won't be 0.3 anymore. It will be 0.1. So we're summing up all these, the accumulation from all these full intervals plus a partial, the accumulation from part of an interval. All right, does it make sense? Okay, here we go. Brains on. Hopefully that all makes sense. So I'm going to, same graph, I'm going to switch to left, okay? Switch to the left side approach for building the step function. But I still have these delta x intervals of 0.3. Okay, so AX is the accumulation of the quantity starting from A and terminating at X. We want to represent A of 1.2. That was the easy one, right? How many things do we add together for that? We're going to add together 4 bits of accumulation, K delta X, 4 times, right? For the 4 different constant rates. But what specifically are those rates? Okay, so those are from the R function, right? Each of those rates comes from the R function. Again, we're using left now, using left. Okay, so what is the first rate? R of what? The first rate is R of what? 0. The next rate is R of 0.3. And I'm going to write that as 0 plus 0.3. You'll see why in a second. All right, next rate, K3, is R of what? 0.6. And I'm going to write that as 0 plus, isn't that plus 2 delta x's? So plus 2 times 0.3. And that gives the 0.6 that you guys said. And then the fourth rate. 0 plus 3 intervals, right? So it's going to be 0 plus 3 intervals, which will give us the 0.9. So 3 times delta x, which is 0.3. Do you follow? So what are the R values on the left side? 0, 0.3, 0.6, and 0.9. Those x values give us the 4 rates that we need to use to calculate the accumulation. The way I wrote it was, so now in terms of A and delta x. So in terms of A and delta x, that's why, so this is why I wrote it the way I did. Let me write this one again. This is 0 plus 2 times 0.3. And then 0 plus 3 times 0.3. So in terms of A and delta x, what R of what first? A. Isn't it? And then? This will be A plus 1 delta x to get to here. And this will be A plus 2 delta x, A plus 3 delta x. I think, oh good, I get to fill those in. So A plus delta x. Okay, I hope that the little conversations are about what we're doing. So now we need a generalized, if we're going to use summation notation, we can let J be the interval number. So this corresponds to J equals 1. This is the little bit of accumulation for the first interval. This will be the little bit of accumulation for second interval. Notice how many delta x's I add to get to the left side of the second interval. How many? 1. How many delta x's do I add to get to the left side of the third interval? 2. And then the fourth interval? In the fourth interval, I had to add 3 delta x to get to that left side to define the rates to calculate the accumulation. So can you figure out a general formula then in terms of A and delta x? What are we plugging into the rate function to get the left side of the jth interval? That's what we want. We want the left side of the jth interval. A plus j delta x? Great, we're going to go a plus a number of delta x's that's one less than whatever interval number we're in. Should make sense. This takes us to the left side of the jth interval. This is the left side of the jth interval. Okay, so this works if our current x value, so this expression works if we land, what, on that end of an interval. We just saw another example where we didn't, so let's work on that example. All right, so can we go a little bit late and I'll give you the time back on another day? This is really important, okay? If you need to slip out, you can watch the video, just do so quietly. Okay, thank you. All right, here we go. So now we want to talk about a of 2.2. And what was the difference with 2.2? We end up in the middle of an interval. So we're going to add a bunch of full intervals together, right? But then we're also going to have a little bit more, right? We have a bunch of full intervals. So how can we write those full intervals first? So this is a little accumulation from part of an interval. Okay, so we can use summation notation for the first 7 terms. It's the same thing we just did, but now 7 instead of 4. 7 bits instead of 4 bits. Okay, so it's the same thing. But now we got 7 bits, r delta x plus r delta x instead of 4. But now we want to add this little extra amount. So how much is this little extra amount? Use symbols, right? Use symbols. What's the rate going to be in this last interval? I haven't heard anyone say it. K8, it's going to be K8, it's going to be the rate in the 8th interval, times what? 0.1 instead of 0.3. 0.3 is our standard delta x, but this is a smaller interval, so it's going to be K8 times 0.1. All right, so let's see how we can rewrite that. Isn't K8 r of 2.1, that's K8, times, that's K8, times our current value of x minus the left side of that interval, right? That's where that 0.1 comes from. So what is 2.1 relative to 2.2? What is 2.1? If our current value of x is 2.2, then what is 2.1? That's something we've done. What is that? The left side of the current interval, isn't it? So that's left of 2.2. So this is our rate at the left side, or K8, that's K8, and then this is the smaller delta x, right? The smaller delta x. Okay, let's put it all together. Here we go. What's that? A, starting value of x. What's that? The current value of x, where we're accumulating to. We're going to accumulate starting from A to x. What's that? Left x, the x value at the left end of the current interval. Okay? So what is a of x? It's the sum of bits for the full delta x intervals. We talked about that. Plus a little bit more. Probably a little bit more for the last partial delta x interval. And how do we get the sum of all the bits for the full intervals? We worked that out, and we got this expression here. The question is, how many full intervals are there between A and the current value of x? Who remembers? How many full intervals do we have from A to the current value of x? Some of you remember. That's that floor function we did, right? That's how many full intervals we have. And then we have the little bit more. It's going to be the rate plus x minus. So the rate at where? The rate at where? For that last partial interval. the rate the left side, and then to get that little part of an interval, it'll be x minus left x. Okay, we did it. Do you get it? Watch the video over and over again. Come to office hours. You need to know what everything means. Study.